Linear probabilistic modeling is a statistical technique for producing a predictive model that minimizes error. This sees extensive use in calibrating sensors because it allows engineers to use a smaller, more easily obtained data set for calibration purposes. Moreover, the process can be extended to nonlinear data sets. The least squares problem states the error of a modeled point is the distance from the point to the vector space containing known data. This distance z is found by taking the square root of b hat minus ux quantity squared. Also, a Taylor series accurately represents any function, including the perfect model of the data. Since we only want a linear model, we take the first two terms of the series and truncate the rest. This is where the error in the linear regression derives. Lastly, we replace b hat with the truncated Taylor series, take the total derivative with respect to the Taylor series coefficients, and set this equal to 0 to minimize error. Doing this across all data points provides the line with the least error in its predictions. But how good is this model? To measure this, we can obtain the standard deviation for the model and confidence interval for any predicted point. Moreover, we can find the coefficient of determination, which tells us how much variation is explained by the model. This happens to be the square of the correlation coefficient. Linear probabilistic modeling is critical to taking engineering measurements. Many sensors work by producing a voltage when a pressure, force, temperature, etc. is applied, and many of these have a linear relationship between the phenomenon and the voltage output. Unfortunately, the exact coefficients for a sensor's calibration curve are not constant across sensors and even vary with usage. Thus, the first step in measuring anything is always calibrating equipment. This requires measuring a range of known values. For example, balance weights for a force gauge, boiling or freezing liquids for a thermocouple, a manometer for a pressure transducer, etc. The lattermost of these is shown as an example here. Once the data is gathered, a linear probabilistic model is created via linear regression that predicts the expected experimental values based on the voltages read and provides a confidence interval for these measurements for the purposes of reporting uncertainty. The predictive nature of linear probabilistic modeling is essential. Not every value in a sensor's range can be tested. For example, the pressure transducer calibrated here can read far higher and lower pressures than the manometer is capable of creating. Thus, simple interpolation is insufficient. A probabilistic model is necessary to extrapolate beyond the data with a known degree of confidence. When engineers use equipment to test samples or conduct experiments, they should calibrate their equipment via probabilistic model. Thus, linear probabilistic modeling is an extremely powerful predictive tool and is vital to engineering measurements. Without it, research engineers could not calibrate their experimental equipment. It is a means to predict values beyond a data set, and while it deals only with linear relationships, its principles can be extended to nearly any relationship.